Thanks for coming, guys. Just to start things off, does anyone have experience actually running Cassandra? Okay, a couple. Okay. So we're going to start the talk. We'll do an introduction to Cassandra, as well as how Cassandra is architected, just kind of the basics of how Cassandra cluster works. Then we'll cover data modeling a little bit. The reason we'll dive into that is we'll come up with kind of a fake use case, and then there's a demo at the end and a GitHub repo where you can download the code for it.
Sure. Quiz?
I can think of one.
There you go.
So I'm Nick. I work at DataStax. DataStax is the commercial company behind Apache Cassandra. So we have an enterprise database platform built on top of Cassandra. We have a monitoring and management tool called OpCenter, which is what I work on. Besides that, I organize the Austin Cassandra Users Meetup. We meet in this room every third Thursday of the month. So come by on Thursday, 3 days from now.
How many people do you have show up for that meetup?
Between 10 and 20, depending on what the topic is.
I don't feel bad. We're good.
Yeah.
Awesome. That's a much bigger technology, so we're actually pretty good.
Well, hopefully more now that I'm giving this talk. So.
Good.
So yeah, we've got a talk on Thursday. A local company, 46 Labs, is presenting some of their uses of Cassandra. So that should be good. I've been working with Cassandra for 4 years now. Before I was at DataStax, I was actually at Rackspace, and I was working with Cassandra there as well. So yeah, I guess with Clojure experience, OpCenter is a, like I said, a monitoring management tool, and what OpCenter does is actually runs agents on your Cassandra servers, and those agents are written in Clojure. The reason being they need to interact with Cassandra, which is a Java platform. So interacting with the JVM, you kind of have to be also on the JVM. And because we didn't want to write Java, we decided to go with Clojure instead. So that's how I kind of got into Clojure. Because of that, I've been writing Clojure for probably 3 years now. I'm actually the maintainer of the Clojure.java.jmx library because no one else was doing it and we needed it. So, Cassandra. Cassandra has been around since, I think, 2007 or 2008. And it was open source by Facebook, but Cassandra is a database built from two main white papers, one released by Amazon called the Dynamo paper, and one released by Google called the Big Table paper. And what Cassandra really does is take the kind of cluster architecture of Dynamo and the server architecture and storage format of Bigtable. So that's not particularly useful unless you know those papers, but just a little bit of background. The main idea behind Cassandra is that it's a shared nothing, completely peer-to-peer architecture. So there's no masters or primary nodes or special nodes. All nodes in the cluster are essentially the same. The reason for that is because it scales linearly. So when you want to, so this is just our marketing slide that has all the users of Cassandra in an image that you can't really see. But lots of people out there using Cassandra. So as I was saying, the architecture of Cassandra is that all nodes are the same. When you want to, scale out your Cassandra cluster, you add more nodes to it, and it's pretty much generally that's simple. It's linearly scalable. Netflix has a blog post out there. If you're interested in that kind of thing, I encourage you to read about how they scaled to 1 million writes per second on EC2, and they've got a nice graph showing as you add nodes, the throughput of the cluster goes up linearly. So that's, and if it's not clear, this is this kind of standard diagram of a Cassandra cluster. You have a ring of nodes. Each of the larger circles there is a server in a Cassandra cluster. So data distribution in a Cassandra cluster. This is kind of a simplistic example, but if you're going to have linear scalability, you have to define how you're distributing your data throughout the cluster. And Cassandra actually uses a technique called consistent hashing, but the basic idea is that each server in your cluster has some token in your token space. And in this simplistic example, the token space is 0 through 100. So you've got one server at 0, one server at 50, etc. And how you distribute data in the cluster is each piece of data that comes in, and we'll get to the data model in a few slides, but each piece of data has essentially what's called a partition key associated with it. And you hash that partition key, which hashes somewhere in that token space, some number 0 through 100. Wherever it hashes, you travel backwards and find the relevant node in the cluster, and that's how you know who owns what data. There's a couple different hashes you can use. For replication, it's kind of, there's multiple replication strategies, but from a basic, that's a basic example. When you want to replicate your data, you travel to the first node that you find after you've hashed your primary partition key, and then you keep going around the ring until you get as many replicas as you want. That's called replication factor, just controls how many copies of each piece of data you want stored. So this is an example of a client writing data to Cassandra. And really this example is illustrating that like I said, each node in the cluster is the same, right? So client connects to any node in the Cassandra cluster, doesn't matter, sends whatever data, and then that node is responsible for determining the other servers in the cluster that are replicas for that piece of data. So in this example, the client connected to the node there. If your replication factor is 3, and that node is not responsible for it, so it forwards it along to the other nodes and then comes back and tells the client success or failure. So failure. Cassandra is a distributed system, so it's completely possible that one of those nodes doesn't respond, or takes too long to respond, or any number of things. So in Cassandra, you have the concept of a consistency level, which basically tells the cluster how many replicas you want to wait for when making a request. So, if you have a replication factor of 3, in this example, you can say, insert this data, tell me there was a failure if not all 3 replicas respond. Alternatively, you can specify a consistency level of 1, and the coordinator will wait on one response and then indicate a success to the client. And the other 2 replicas may or may not write that data. The client doesn't really know what happened. And then quorum, alternatively, is a majority of your replicas. So I've kind of mentioned scalability. Scalability is one of the big reasons that people choose to go with Cassandra, and that's scalability in terms of throughput or nodes in a cluster. But Cassandra is also a pretty good choice if you need geographical scalability. So, for example, if you need to run a cluster in multiple data centers throughout the US, in this example, an East data center and a West data center, Cassandra allows you to kind of intelligently have a single cluster spanning that geographic region. So, in this example, you have 2 separate rings there, but each one of those is part of a single cluster. But the reason they're drawn as separate rings is because you configure replication on a per data center basis. So you say, I want 3 replicas in my east data center and 3 replicas in my west data center. And so there's a couple tools or concepts for working with multiple data centers. In terms of consistency level, one of the downsides of geographically separate data centers is, the latency between them. So you can say, I want to write this piece of data, I want it to end up in all data centers, but I don't want my client to block on the WAN link, right? Because that's extremely slow. So that's kind of what this diagram is illustrating. Client writes into data center east, gets some responses from the nodes in that data center, and then gets a success or failure, and then asynchronously that data is being sent to the other data center to be replicated there. So that's kind of the 5 or 7 minute Cassandra Architecture introduction. Anybody any questions there? Feel free to jump in at any time with questions, guys.
So when it does that distributed replicate, and you do the quorum, it still does multiple replication in each. So if one of those nodes fails, it still finds it. It doesn't have to jump back to data center east to do a find, right? Like in the node, like it replicates to two spots.
Right. The way that what that diagram is trying to illustrate is that it sends the piece of data over the WAN link once, and then another coordinator in the remote data center sends it to replicas in that data center.
Is the quorum per data center, or is it per cluster?
Well, it depends. So I guess I didn't really explain that, but local quorum, that is specifically saying, I want to wait for a quorum of the replicas in the local data center, but not the replicas in the other data center. If you just specified a consistency level of quorum, it would wait on, 6, whatever, 4 replicas to respond.
Okay.
One of them would be in the other data center.
Okay, cool. Thanks.
Cool. So data modeling in Cassandra. Cassandra has this thing called CQL, which is the Cassandra query language, pronounced SQL, which is somewhat ironic, but it is SQL-like. It looks pretty much exactly like you would expect SQL to look, but it is not relational, right? So Cassandra, this is a fairly new concept in Cassandra. It hasn't always had this SQL concept, but really Cassandra, while it's labeled as a NoSQL database, it's not really a NoSQL database. It's a no relational database, right? So when you have a distributed database like that, you lose things like joins and all foreign keys, constraints, and all of that kind of stuff.
Quick question.
Yeah.
When you say NoSQL, do you mean not only SQL or not at all?
Well, that term started as NoSQL and then kind of got rebranded into not only SQL.
Right. That's the question.
Which one do I personally subscribe to?
Well, when you use, in which sense do you use it?
Well, the term was coined by one of the committers of the Cassandra project, and at that time it was meant NoSQL, not only SQL. But it was really, what it really meant was no relation. And you can see that clearly we don't mind SQL that much. So some terminology. These should be fairly familiar, most of them at least. Keyspace is somewhat analogous to a database in a relational database system. A keyspace is where you configure things like replication options. So you say, I have a keyspace, which is a collection of tables, and I want this keyspace, replicated 3 times, or 3 times in data center east and 3 times in data center west. Table, row, column, all what you're familiar with. Partition key and clustering key are the more interesting parts. So, like I said before, partition key is what determines the distribution of your data. So that's the part of your row that's hashed to determine where the cluster belongs. Clustering key is what determines how the data is stored on disk. So more specifically, how you'll be able to read your data back out, right? So for example, if you want to read all your rows in order of, in alphabetical order ascending, that's going to be part of your clustering key, because when you read that data off of disk, you want it stored in alphabetical order ascending. And I think that'll be clearer if it's not once we get to concrete examples. Data types, this is copy-pasted from the SQL shell, which comes bundled with Cassandra. You can load it up if you've downloaded it, but all your standard data types. The interesting ones are counter types, which we'll actually have an example of when we get to a concrete example. And then also, it's also worth noting there's a couple collection types, so map, set, and list. Which are fairly recent to Cassandra, so if you've looked at Cassandra before and haven't seen those, definitely worth checking out. I don't have any examples of those in our examples, but they're what you would expect.
How about INET?
IP address.
Okay.
So just a couple advanced concepts that I won't go into, but we can, if anybody, if they look interesting, we can talk after the rest of the talk's over, or you can go look them up. But also recently added was lightweight transactions, which basically gives you transactions in a Cassandra cluster. And by transaction, they're called lightweight transactions because it's basically, it gives you a compare and set operation in Cassandra, so that you can have linearizability of certain operations. It does that through a concept called Paxos, which is a consensus protocol, which is way more in depth than this talk. They're a lot more expensive than regular updates to Cassandra, so use them sparingly. Other concepts, atomic batches, basically giving you atomicity across inserting multiple rows in the database. And then user-defined types are actually coming out in the next major release of Cassandra, but I threw them in there, but that basically allows you to compose multiple types into a single type. So as an example, you can create an address type, which includes a street address, which is a text, and then area code, which is an int, and those kinds of things, and then use that address type in your schema. So,
when is that next major release?
So the next major release is 2.1. The current release is 2.0, and it's currently on release candidate 3 of the release process. So hopefully by the end of July, 2.1.0 should be out.
Cool. Pack day.
Yeah. I mean, you can go get the release candidate and file bugs if you find them. I encourage you to. Okay, so we'll dive into an example, which is the demo, which I'll show at the end. First, kind of just the general way you want to think about data modeling in Cassandra. And sorry, there hasn't been any Clojure. I won't get to that, guys. So in Cassandra, the way you do data modeling is by modeling the queries that you want to run on Cassandra. Like I was sort of touching on with clustering keys, you want to store your data on disk the way that it's going to be read back out. That's going to help you optimize your reads, which are the more expensive part of operations in Cassandra. So, and that concept's a little strange, I think, to some people. I think it's where most people get tripped up on when they start using Cassandra. Generally, people, or at least in the relational world, people throw a bunch of data into a database, then just start running ad hoc queries on it as they come up with them. But you can't really do that with Cassandra. It's not going to work well. Definitely don't be afraid to denormalize, and you'll see that in our example. One of the driving principles behind Cassandra is that disk space is cheap. So don't be afraid to store things multiple times if you need to store them multiple ways in order to read them efficiently. And you'll probably get your data model wrong the first time if you're new to Cassandra. Just have to iterate on it. So the example I came up with is a Last.fm clone. Hopefully everyone's familiar with Last.fm. Anybody not familiar with Last.fm? So, building this simplistic clone of Last.fm, these are some queries we might want to run if we were developing Last.fm. So, seeing which, the most recent songs that users have listened to, the most popular, or the songs most listened to by a user, and essentially the same queries, but with an artist instead of a user. So starting with the first one, this is kind of an example of really one of the most popular data models in general in Cassandra, and that's time series data models. So really any sort of data model that is a stream of events. So in this example, a user listening to a songs, each listen has a timestamp associated with it. And you insert that into the database. And so any sort of data model like that is probably 90% of use cases people have with Cassandra. In this case, it's immutable, which is good fit if you're using Clojure, but also a good property for your data model to have for Cassandra as well. So, like I said, starting with queries, this isn't necessarily CQL, but this is what you might imagine a SQL query for that query I just described. So you can see from this query, the where clause is really where you're going to have your partition key in Cassandra. That's the piece of data that gets hashed to determine which nodes in the cluster own a specific piece of data. So if you don't know the partition key, you don't know where to go to get data. In this example, clustering key, which I touched on earlier, is play data. That's the order that we want to retrieve our data, so it's also the order that we want to store our data. So this is CQL. If given the query we just had on the screen, this is the create statement for that table, right? So you can see a couple things in here. Primary key at the end of our column definitions there is defining both the partition key and the clustering key. Just lots of different keys. So the first part of that primary key is the partition key, so username in this case, and the second part is the clustering key, which is when the user played a certain song. And so what that's saying is distribute my data with the username column, order it by the played at column. And then below that you see we say specifically order it in descending order. Questions on this? So that isn't actually the best way we can model that table. So in this table, the partition key we've picked isn't really the best one. Who has an idea why?
Because there could be lots of John Smiths.
Well, we're assuming username is unique. You have a sign-up process where you pick a username. There's no duplicate.
Doesn't really match well.
Basically, right. Using username as your partition key means that a user's entire listening history is going to be stored on the same 3 replicas in the cluster. So, if a user has listened to, 2 billion songs, 3 replicas of your however many are serving all of that data, whereas another user who's listened to 3 songs has 3 replicas serving that data. So you don't get a good balance across your nodes right there. So the next slide shows really the most common way people try and solve that specific problem, which is basically artificially insert a time window into your partition key. So in this example, we've added basically a year and month column, which is, just like it sounds, the year and month that a user listened to a specific song, and added that to our partition key, which is what that double parenthesis syntax there means. I know you guys aren't scared of parentheses. So what this is doing is basically saying for each month of listens that a user has, each month will be stored on a different set of nodes in the cluster. So it distributes that user who had 20 billion listens, probably not all in the same month, evenly across the cluster. So this is copied and slightly modified, but mostly just copied out of the demo I'll give later. But this is an example of running a select query from the Cassandra SQL shell. You wouldn't want to do select star on a live database, obviously, but it worked for these purposes. And here you can see kind of what I'm trying to illustrate with the difference between partition key and clustering key. So in the orange box, we have our partition key, which is unordered, right? It was hashed and then distributed around the cluster randomly. There's no ordering to the list of usernames there. You can't. So what that means is you can't query for username greater than A and less than C, right? Because it's not in any specific order through the cluster. But our played at columns within a single partition are ordered. So I can say, give me all listens by Nick after 3 p.m. Get that? So yeah, that's the first query. The next query we want is give me the songs Nick listens to the most. In our example, we've already decided to distribute listens by month. So specifically in this example, we're saying give me the songs Nick listened to the most in July. Kind of the same. We take the same approach here that we did before. Parts of our where key are our partition, or where clause are our partition key. The difference here is if you were doing this in a relational world, you would have this order by clause and it would work fine. In Cassandra, counters are kind of a special case. So they have a couple of restrictions. First, they can't be part of your primary key, which is where you define your clustering key and therefore ordering. And they have to be the only column not in the primary key. The reasons for that are due to the storage format on disk, which I could get into later if people really want. But basically, it's just a known limitation. Maybe it'll be lifted in the future, but I don't know about any specific plans. So, I mean, that kind of places some restrictions on our data model. So, so this is what we have for modeling counts of songs. You can see, you know, play count is the only column not in our primary key definition there. Username and year and month are our partition key as well, just as before. And then the other two are in our primary key. Not specifically because we want ordering on artist or song, but because of the restriction that they have to be part of the primary key. So there's kind of a problem with this data model. Anybody have any ideas? In terms of serving the query that we want.
They're not indexed by month or year. Isn't that good?
No, they are. Or, I mean, well, they're not ordered by year and month.
Is that selected enough?
Well, in our query, our defined query was, you know, give me the songs listened to by the most songs listened to most by user in July, right? So you are already limiting your query to a specific month. So the issue is, like I said, counters can't be part of your clustering key, right? So our query we want is songs listened to most. So we want to order by song count descending, right? But we can't do that. So you can see in the example here, you know, you have these counters stored in your table, but there's no specific ordering to them. And you know, the result of that is, in this specific example, we have to load the entire data set and do the sorting client side. So, you know, that can be problematic if the data set is gigantic. We're assuming here, you know, the number of songs listened to in a month isn't gigantic, but if it is, this table might need to be limited to a day or a week or something like that. Does all that make sense? So the next two queries were basically mirror images of our first two, but with respect to artists instead of users, right? So given an artist, what users have listened to their songs recently, or what are their most listened to songs. And we won't we won't do the same exercise because it's the same, but basically what I'm illustrating here is denormalization, right? So these are the exact same columns that we just had in our user history table. And in a relational database, you would normalize and you would have those columns stored in an external third table and references to these tables, and you only store the data once. But you know, in Cassandra, you don't do that. You just insert the data however many ways you need to query it. So we're inserting the data, same exact data again, into the artist history table, so that when we query for the most recently listened to songs, we can get that efficiently. So same as before, counter column family or counter table. Okay, any questions on that? Good, all right.
I have a question.
Yep.
On the query index part, can you have like 10 criteria for the primary key? I mean,
so
what's the guide?
You can. The primary key, so the first part there, the partition key in the second set of parentheses is how you determine where data is. So whenever you're doing a query, you have to know those pieces of data. So you can't say, you know, select artist select artist and album where artist equals blank and not give a year and month as well, right? And so the second part there, the clustering columns, Those are hierarchical.
Okay.
So you can't order by song and leave out album, right? So in this specific example, we don't care about ordering; they just have to be in the primary key. But you couldn't, if you wanted to, say, give me all songs order descending and not specify also an album.
So they're hierarchical in order. So albums
In order.
top,
Right,
different
right.
song.
Yeah.
What if I want it to be partitioned by the geological server that we have as well? So artist, year and week, and then on the east node.
So I
Can you
didn't.
do that?
I just forgot, but I didn't include that. But that is specified at the Keyspace level, right? So
Okay.
all these create statements that we've given examples of. First, you would create a keyspace and say use keyspace y, and then create these tables in that keyspace. So when you create the keyspace, you say all tables in this keyspace I want replicated to data center X, Y, and Z.
But it's at the table level. I can't.
It's at the keyspace level.
Okay, so the key will take the locality of the insert into. Is it based on the
client
insert?
or
Yeah, when the data comes in, if I want it to stay on that cluster
well,
geographically where it was inserted, because that's probably closest to where it's used. Is there a way to do that kind of thing, or?
well, so I mean, generally you'll have, I mean, no, but generally you'll have you'll have your data in all data centers, but clients will know which data center they're a part of and only send data to those nodes. They know which nodes the data
Okay,
centers
so
are
the
in.
replication is the side effect in a sense. The query will resolve locally because it won't have to go to a replicant probably.
Right, based on your consistency level and your replication settings.
There's
It's
no
not-
way for me to know the node I'm inserting as a client.
No, there is. I mean, that's transparent to application developers generally, but like I said, the distribution is determined by a hash. So
Okay.
clients can also
Good.
compute that hash in order to determine which nodes
Okay.
are the replicas. And the Java driver which we're talking about does that to make things slightly faster and avoid a network hop. But that's all transparent.
Okay. Thanks.
All right, Clojure. So building blocks for a Clojure client, or at least the Clojure clients that exist now, are the Java driver, which is a Java client developed by DataStax, but it's open source, and a library called Hate, which is developed by just a community member. So the Java driver is just a fully featured Java client. Clojure drivers wrap that, as is common with most Clojure projects. It's got tons and tons of features. If you're looking for something in the Clojure client and can't find it, looking in the Java client and seeing where it is there might help. I won't dive into the details of connection pooling and failover, but there's handling for all of those kinds of things. Hate is I'm not positive I'm pronouncing that correctly, but I don't know how else you would pronounce it. Hate is just a DSL for CQL. So similar to Korma, if you use that for relational database access in Cassandra, all it does is basically let you idiomatically use Clojure code to generate CQL strings. You can see the example there. So both of these clients, these are the two main clients out there for Clojure and Cassandra now are built with the Java driver and Hate. Alia is written by the guy that wrote Hate as well. Casa Forte is written by a group or a company called Clojure Works, which also write a bunch of other libraries, like client libraries for Mongo or other databases. So maybe you're familiar with them. But as a side effect of both being essentially wrappers for the Java driver, they aren't particularly different. So just some example code. They're both using Hate, so the CQL DSL is the same. They each have the concept of cluster. Yeah. So when picking one, I don't have much advice besides whichever one looks nicer to you. So I did the example, the demo application in Alia. Mostly I picked Alia because it has a core.async interface to interacting with it. And I wanted to try that out, but then I didn't have time, so I didn't. But Alia does have, it was on my earlier Java driver slide, but the Java driver exposes an asynchronous interface to executing queries, and Alia wraps that in core.async and also Lamina. So that's kind of why I picked Alia, but besides that, not a huge reason. So Alia, you create a cluster object, which is where you configure everything. Your failover policies, retry policies, load balancing, all that stuff. Not too exciting. You create a session object for that cluster, which is how you interact with multiple key spaces using a single cluster object. Each session has a key space associated with it. And like I was saying, there's multiple ways to query. So you have a synchronous execute API, and then you have specifically the execute async API, which uses the Lamina in the back end, if you're familiar with that, but basically returns a promise, and optionally you can add callbacks. And then, like I was saying, execute chan uses the core.async API, if you're familiar with that. It's definitely a topic for another day. There are prepared statements, so just an example of that. If you're doing the same thing lots, you should probably use them. Some links to Alia. And that's the rest of the presentation. We have a little demo, but yeah.
The slides.
Oh, I'll put them on SlideShare, and I'll tell Sam to send out the link.
Yeah, sure. I'll send it out to the discussion board and the email to everybody.
Questions before I do the demo?
Yeah, back on the code, there was 2 sessions you created. The second one didn't have a key space. Does it give it a default one or something?
The first one has a key space. I mean, the first one doesn't have a key space.
Right.
It doesn't, it doesn't give it a key space, but then there's a use key space method.
Okay.
So before you actually run any queries, you'll have to say use key space X.
Okay. And then, it's been a while, but if you want a local dev instance, what does it do with all the clustering stuff when you tell it I'm working in multiple key spaces? Just run on your laptop or something.
Well, I mean, you can have multiple key spaces on a single node cluster, right? So that doesn't, really come into effect. In my example, I'm actually, in the demo I'll do in a sec, I'm running 3 nodes locally. You can run multiple Cassandra nodes locally.
You can run multiple.
Yeah.
Okay.
So, and if you were only running 1, you would want to set your replication factor to 1, set to 3 in the demo. So take those things into account.
So that's all configured on the install, and you have to allocate some disk space to it and stuff like that?
There's,
because the reason I asked is you mentioned that the storage is related for the counter to how it's stored on disk. So
Yeah, so I mean, I'm running 3 nodes locally, so each one has its own directory that it's storing data in.
okay, it's just a directory. It's not actually. You don't have to partition the drive.
No.
Okay.
Yeah. So these are all the stuff the demo was built with. That's the GitHub link if you want to look at it. It's already up on my GitHub. But the first one there, CCM, stands for Cassandra Cluster Manager. And it's just a Python lib for running multiple node Cassandra clusters locally, right? So you say CCM create -n3 and give it a name, and you've got a 3 node, Cassandra cluster on your machine, and you tell it to start up, and it's as easy as that. Other things built on Alia, random Clojure and Hiccup. Standard web server stuff. You guys are familiar with that. I started doing Clojure script for the demo, and then it was late in the day, and I realized I was diving down a rabbit hole I wasn't going to get out of, so I just went with Hiccup, just templated HTML. And then Least is just a thin wrapper around the Last.fm API that is easy to use. More links, Cassandra, all that's just Cassandra stuff. Actually.
I have a question. Do you guys have like a equivalent to like a PG admin or PHP admin or anything like that?
Well, so that's kind of what OpCenter is.
Okay.
OpCenter is less of a data browser and more of a cluster manager.
Okay.
But yeah, for just browsing data, there's the SQL shell,
Okay.
which I'll show. Cool. So, is that visible at all? So yeah, that's the GitHub page for the demo. Has instructions if you want to run it. CCM, you need an API key. Yeah. Oh, this is, I don't know what that error means. This is OpCenter. What the project I work on and what I was just saying is kind of the same as like, oh, all my nodes are down. I don't know why it says all my nodes are down. But anyway, this is, Last.fm if you haven't seen it. This is what we're going to try and imitate. So in our example, I already have a 3-node cluster running, so get to see CCM in action. CCM status, you see all my nodes are up. Or maybe not up. Live demos. I think they probably died because I'm running 6 JVMs right now on my laptop. Perhaps I should stop some of them. Stop ups. Okay. So got a cluster up. This is the SQL shell. You saw some copy pasted code out of there. Got a cluster. All it has is it's got an OpCenter Keyspace. Here's a good example of creating keyspaces, different replication strategies. And it's got a system Keyspace, which Cassandra uses internally. So this is the Git project for the demo. To run it, all you do is do line ring server. that'll start demo. It'll create the tables we just talked about, start the web server, and the line ring plugin actually will open the web server in the browser for you. So that's kind of cool. It might take a little bit. You can look at the code. So this is the code for the web server. Normal, oh, there it goes. Normal ring and composure stuff, some routes, app, then a bunch of, all the rest of this stuff is hiccup HTML templates. So here's my very pretty demo. We have a function to load a bunch of data from Last.fm because we don't have any data. So I give it a username. And then you can go check out the log, and it's loading all the tracks I've ever listened to from Last.fm and storing them into our tables. It's only going to load 10 pages, otherwise we'd be here all night. Anybody else have a username they want to load? Any Last.fm users? No? All right.
I used to.
What's your username?
C's, C-E-E-Z. Charlie Echo Echo Zebra. I don't know if I killed the account or not. I mean, I had it for 10 years. I used to use the Scrabbler. I got tired of that.
There it goes.
There it goes.
You only got 21 pages compared to my 223. So yeah, then, I mean, I did this weekend, so it's not very pretty or usable, but this is just a quick link to a user page. So that's my user page that we just finished loading. You can see there's the favorite songs list being served by our counter table. Below that is our recent listens being served by our user history table. Matches what we just saw in Last.fm. Pretty simple. We can go to the shell. And use a keyspace. And select, oh, there's a bunch of C's rows. Got a bunch of song counts, which are not very high. And then there's a link to a random artist, which I knew would have data for it, so that's why I picked it. There's an artist and who listened to it, which is only me, because there's only 2 users in here. But yeah, that's about it. You can see how we're formatting things in the URL. So artists are actually broken down into per week partitions. So I've got a 2014 week 29. If I go back to week 28, I didn't listen to that artist at all. Oh, 287, sorry. I didn't listen to week 27 either. But yeah, that's it. That's the demo.
So 2014-W2.
Yeah, that's how Joda time formats it.
Okay.
I'm using the CLJ time wrapper.
Okay.
All the database code is in db.clj, so to see some alia code in action, you see we have this track played function, which is running all of these insert statements above it. For getting history, so you can see for getting history, we're loading the entire row of username and year and month, and then we're filtering it or sorting it by count and taking the top 10 all on the client side. So our database isn't doing any of that for us.
So track plate is the insert.
Track plate is the function inserting all the data as we load it from last.fm.
Okay. So you just call all those other inserts because those are the denormalized things that map to the queries you want in your system.
Yeah, each one of those is inserting into a different table. And it's actually using the execute async function I mentioned, which uses Lambda in the backend, but really it just looks like a promise. So we do a bunch of asynchronous inserts to all those different tables, and we just block on each promise that was returned.
Okay. So then after the promises are done, you dereference it.
Right, that's how you block on the result of a promise. Yep, that's it. Questions on Cassandra or Clojure or whatever else?
For that particular thing, you denormalize, so you get the normal data stored that you see. Disk is cheap, but how about all the indexing and stuff? What's the kind of overhead that you can expect?
Well, so it's not really indexing in the sense of a relational database where you have a separate index, right? So it's storing the data in that format on disk. So, we ordered things by played at, what time I played it at. So on disk, when Cassandra goes to read it, each row of the table is stored in order, descending by played at. So it just does a single disk scan to load up all the rows and serve them back.
So, and they're literally stored sequentially on the disk, so the read is just the read at spinning around? Or?
Yep, that's generally the idea, is that you want to serve your reads by a single disk seek in Cassandra.
And then the hierarchy part is the same way, right?
Right, so if you have multiple things in your clustering column, they would first be ordered by artist and then ordered by song.
Right, but they're still in sequence of those two criteria.
Yep.
Okay. Cool. That's cool. It looks really easy to use.
Alia was pleasantly, so I guess I'll mention, we're not using that in the OpCenter product due to it being backwards compatible with things and not using CQL yet. But yeah, Alia is a million times nicer than what we are using, so I was pleasantly surprised.
So you could rewrite it in a weekend?
If OpCenter wasn't backwards compatible with so many versions of Cassandra, yes, I could.
There you go. OpCenter version 2.
We're on version 5.0.
There you go.
Damn backwards compatibility.
Yeah, it's the worst.
Cut the cord.
Yeah, about that.
That's cool though. So for a lot of the customers, you said that they were storing time sequence kind of data. What's some of the other kind of stuff you see people doing?
Other things, that's kind of the data model that Cassandra fits really well. Anything that's ordered and you can do a single disk seek to read it back fits well with Cassandra. There are plenty of other ways to store data. So, like, for example, our counter comp family isn't stored in order. We just read the whole thing and sort it client side. But that's something where that data model wouldn't work if we had, millions and millions of songs in a single row and we had to load them all into the client and then sort them. So there's plenty of other data models, and they're used when it's okay to use them. Like in our example, there's not that many songs, so store it in Cassandra, read it, and filter it. And plenty of people do that. And then the other, reason you use Cassandra is for things like the geographical replication properties and things like that. So you might not have a data set that needs, that time series aspect or anything, but you need that multi-data center replication stuff. So put it in Cassandra.
So do you see most people using it in conjunction with a relational database for those other kind of scenarios where they need that count to be super quick, and then they do the time ordered stuff
It depends. Later? Like I had a comment on the GitHub project, like if I was actually writing this, I wouldn't have stored those counts in counter columns. It would probably be a batch analytics job that ran weekly and computed them and did store them in, sequential order and things like that. So one of the things with Cassandra is, there's a million data models that don't fit on Cassandra, but most of those data models can be modified so that they do fit on Cassandra. So the reason that time series kind of data model is so popular with Cassandra is often that's how you change your existing data model to map on Cassandra. So instead of updating columns, you keep a log of updates to some object in the database, and so then you have a time series data model. So this thing changed at time X and changed again at time Y.
So often do you see like the business requirements forcing the schema to change? Because a lot of people still have that SQL mindset, and they add a query and it's easy. Like you said, you have to know your query is going in to design your data model.
Once people have decided on Cassandra, generally they've accepted that it's not a relational database, and whatever they have currently stored in a relational database is going to change.
Mm-hmm.
And so usually what drives that is scalability needs or those geographical replication needs.
So, like on a common disk today, 4 terabytes, what would be the average kind of application that you would see with that? Is it just only big data, or do you see smaller people using it, but they're using crap loads of tables, so everything's optimized?
Literally everything. Some people are running multi-hundred node clusters with a terabyte on each node. Some people are running 6 node clusters with 10 gigs on each node. So
well, for like caching and stuff, memcache, does it have an analogy to that, or does it do it automatically?
So there's a couple different, Cassandra has some built-in caching, not in the sense that you usually use things like memcache for, which cache everything in memory. So it has a key cache, which basically caches disk locations for things, and it does have a row cache, but it's not particularly useful. It's not a write-through cache, so updates invalidate it. But generally, the thing with Cassandra is if things are slowing down so that you think you need a cache, often the answer is just add more nodes to your Cassandra cluster, rather than trying to stick a cache in front of it, because you can just scale the cluster and get more performance.
Okay.
That's not always true. Cassandra is persistent, so all writes do go to disk, and compaction and other things like that, which I didn't go into, happen, and reads will have to go to disk. So some people stick a cache in front of it just to know that everything's in memory. But
so the read is limited by the disk speed, basically. Would that be the correct statement?
yes,
Okay.
if it's not cached by the OS page cache, or if it's not in the row cache or in a mem table or whatever. But
and that's why you get the linear improvements by adding nodes, because you got 1,000 reads happening.
right, you've got X more disk spindles.
Cool. Anybody else have questions? I was like hogging the question.
Yeah, I got a question. You may have mentioned this, but for small data sets, is latency comparable to a relational database?
Assuming you model your data,
Yeah.
correctly, and for how Cassandra works, yeah. Like I said, if it's a really small data set, it will already be in the OS page cache. So
Yes, that's what I'm getting at. This would be for like the config data as opposed to the working set.
Well, so you can't there's no way now to for Cassandra to tell the OS this is a small hot column family, put that in the page cache and don't put this other data. So if you have, a small data set and a large data set working side by side, they can interfere with each other, but you're limited by the speed of your disk, right? So as fast as you can do a single disk seed to read the data.
Cool.
I got stickers up here if anybody wants them. Apache Cassandra.
Nice. Okay, I'm got some from.
I've just been sold.
Stack.
As a Clojure sticker.
I threw a bunch of them on that desk up there last time we had like standard meetup. I don't really know. So.
Sam, before we go off top, I have the follow on from last month's talk I'd like to do real quick.
Sure. Let me shut down a couple things. Thanks to Nick for giving a
Thanks, guys.
talk. I have to quit a whole bunch of things first.
Yep.
Not because you can't see them.
Now I get you.
There's just like crap loads of stuff running. Earlier today I had like 150 tabs open in the two browsers. Exceedingly insane. You're out of control when you have so many processes running from a web browser that your machine slows down when you have 16 gig RAM. Cool.
Sweet. Thank you. I will actually have a connector next week.
All right. Yeah, the other day I had cursive running, PyCharm.
See if this just works.
Postgres.
Yeah.
And Xcode. And it was still going strong. I was paging some, but it's a static disk. I wasn't really noticing.
What's going on here? Max or hard?
That $2,000 was worth it. It was like the
I
test
had to
case.
do the AirPlay, not connecting it.
Oh, you did?
Connecting it.
That one was like 3 months old. And
How did you
my wife dropped her. She was gonna get it.
No, it used to be on Wi-Fi for AirPlay to work.
I'm getting it. You can have mine over. The old one was a Retina 2. It was just the older chipset. This one has like an hour longer battery life.
Password.
You dropped yours. You get the hand it up. I took care of mine.
They were waiting for me right on my desk, already
Yeah.
set up.
Yeah, one of my friends was giving me crap. She's like, what?
Yeah, I didn't
I'm
get
like,
the connector to work.
she stays at home.
Yeah, it was working
I'm not gonna spend
last
$2,000
month, which is
on
why I
that.
asked for his laptop, because I can't use, I don't have a.
Mine's actually
You can use mine if you just, I don't know what you're loading.
I mean, all I'm gonna do is pop up a web page and a GitHub library.
You can use mine.
Okay, we'll just do that then. It's easier. Sorry to make you shut down everything for nothing.
Aw. No worries.
I'm a terrible person clearing your hot cache.
It's okay. That just means Safari will boot up faster.
Pretty good.
So one thing to do is to base it up quickly and move it.
Oh, yeah.
This one had vibrant disk installation.
Sweet, okay. So I just wanted to show you guys real quick something I discovered after last month's talk and something I built in the interim that's related. So the first one, you don't have control rebound to caps lock, you terrible person.
I don't know what that means.
Hello.
I do have control bound to caps lock.
You do? Okay. Max.
Oh, you're thinking it's command on Mac.
Yes, I'm thinking it's command on Mac. GitHub pushux. So last month, I remember that Norm was up here and he was trying to show Clojure docs examples from the REPL and trying to pull Clojure docs examples from the REPL. And he was surprised that he wasn't able to use the cdoc function to go and pull down examples of function usage and doc strings and commentary from Clojure docs. And the reason for that, it turns out, is it's not in Clojure REPL or the Clojure REPL library. It's actually in Darkrone's Clojure docs client. So if you go and throw this in your lean profile, you can just go require the Clojure docs client and go pull function documentation into your REPL and function examples into your REPL and print them in line, which was pretty slick. The announcement, Command L works, nice, which you may or not have seen, is I got together with Andy Fingerhut and we did a new version of the Clojure cheat sheet that's not live on Clojure.org because Rich has to sanction it in weirdness, but it is live here, grimoire.artem.com.
Did you post this on HN this weekend?
Yeah, this made front page on HN yesterday.
It made my whole freaking weekend.
I did not post that.
It was awesome.
Someone else posted that. It hit number 5, and I was just like, my Saturday's made. I'm done.
Yeah.
Congratulations. So you dropped the mic with it.
Yeah. So
It's awesome.
it's the same as Andy's main cheat sheet. I did almost nothing to the front page. If you look at the build script, it literally builds Andy's cheat sheet, does 3 seds, and copies it in place. So there's very little different here. You can just type in lines, so let's say true. And you can see that it pulls out the subset of the cheat sheet that mentions the word true and the category that's in. Let's check for the arrows. And you can grab the arrows, and if you click on the arrows, usually the cheat sheet will take you to Clojure docs and Clojure docs examples for and documentation for Clojure 1.3. So Grimoire has 1.6, 1.4, and 1.5, and nothing older than that. I'm still working on the examples contribution system. It does not quite work yet because of the way my build system's built, but it should be working very, very shortly. So I will totally admit that I'm pimping something I built up here, but I think that it's pretty awesome. And
Actually, we were talking about this earlier.
Really?
And Sam said, oh yeah, we should get this guy.
Okay, well.
I mentioned it.
Yeah, because you weren't here yet, and I was like, we should have him talk about it next week.
Oh, yeah, no.
Next meeting.
So just.
Talk slow so Sam can.
So this is what I built. Unfortunately, because it's built on top of Jekyll and is entirely a static site, there is no API, there is no server, there's no nothing behind this. It's just flat files that you can go edit on GitHub, and if you click on the Please Add Examples link, it literally bumps you over to GitHub on the edit this inline page and tells you fork this shit. So, yeah.
That's cool.
That's all I got.
Hopefully Rich approves that, because that's freaking nice.
So,
Yeah.
I'm going, spoilers. I did not say this. I got some help from Pure Danger. What's his name? I'm
Alex
blanking.
Miller?
Yeah, Alex Miller. Alex threw me the database that's actually behind, or an SQL dump of the database that's behind Clojure docs, and went, here, if you need this. Also, I'm working on a better doc system for Clojure in main that Rich hasn't signed off on yet, so it doesn't exist as far as the rest of the world's concerned. So my guess is that this is gonna be a stopgap, and hopefully Rich will approve whatever it is that he's working on, and that'll drop, and I will pull this in favor of whatever the new official docs are. But new official docs do not exist yet and are still skunkworks, so here these are. I hope they're useful. Thanks.
It's super useful. Thank you.
Awesome.